So my name is Mike Segala. So I run a company, SFL Scientific. So we're a data science consulting company. And one of the nice things about being a consulting company is we get to work with a lot of different industries. Specifically here in Boston, we run into finance quite a bit. So finance, like a lot of the other industries, like insurance or healthcare, right, they're solving a lot of very similar types of problems. So the talk basically is going to go through the types of problems that are being solved out there, just kind of high level. We won't dig too deep into specific solutions or things of that nature. I just want to kind of give you an overview of what's happening out there in the space so you can kind of understand some of the kind of techniques and challenges that other people are facing, either in your industry of finance or in other kind of industries that might be related to you. I hate not having a laser pointer. Do we have one of those? Is there? Oh, no, she left. So we're going to kind of touch through 4 very different points of the talk. So this is a long talk, about an hour and a half, so we'll kind of keep it open. If you guys have questions, let's stop so you guys don't fall asleep. Let's keep it kind of dynamic. So the first thing, we're going to spend a good portion of the time just talking about NLP in finance, specifically building kind of an end-to-end pipeline of this kind of classification and extraction pipelines. We'll quickly look at some sentiment and topic modeling, so we'll talk about how that could be related to finance. We'll completely switch gears into some time series things. That will bring us into some more of the kind of more interesting things of deep learning. What is deep learning, very kind of on the high surface, and then how are we using it possibly in finance, and then very kind of different things about portfolio optimization. So, not yet. So NLP, right? So we all, no matter really what industry you're in, right? Call it finance, call it pharma, call it health and care, it doesn't really matter. There's a really common problem out there where we have tons of text data, right? Unstructured, free-form text data, and this is coming in constantly, right? We might have streams coming in every minute, every day, every quarter, and we want to do something with this data, right? You can imagine if you're a fund manager, right? You work at a PE firm or something like that, and you're investing money that somebody gives to you, right? You might manage $10 million, $100 million or something of that nature. And you have all this money, and now you need to invest it into, say, 100 or 1,000 of your different investings that you're putting it into, right? It could be stocks, bonds, could be soy plants, could be coffee. It really doesn't matter. The point is, every quarter or however often it is, these 1,000 investments are all giving you back information in the form of some text, right? It could be PDFs, could be Excel files, could be Word files. It doesn't really matter. But what you have to do then is look at all thousands of these files, pull out information from all of these, and they're structured very differently. And it's a manual process, right? And you're constantly doing this, you're constantly looking into it, you're extracting this information. It's very error prone, right? So it's a common problem, and you can kind of make this relatable to any industry you're in. And the issue is, once you start doing this on a very kind of recurring basis, you kind of run into this rule, right? This business use case rule that says $100 rule, where for every piece of data entry or data verification that a human has to make, it roughly costs your company $1, right? And that's if you do it correctly. If you do it incorrectly the first time and somebody later down the road catches it, it costs you $10 as a company. If you do it incorrectly and you never catch it, it roughly costs you about $100 or more, okay? So if you look at all the data across your systems, about 1% of the time it comes in incorrectly, meaning you never capture it. If you add that into your cost of labor, just doing this exercise of kind of aggregating and looking manually at documents or whatever your text is, it's a several $1 million a year problem, across your firm or wherever you're working, right? This is a huge problem. And this is literally costing you man hours and tons of cost. So what we want to do is we want to completely take the human out of the loop, right? How do we actually build now a system such that it will do this automatically for us, right? We don't want to have to sit there and literally churn through it ourselves. We want to kind of automate this process. So that's what the first kind of use case that we're going to kind of run through here. So the purpose of anything, right, to automate something, we want to make it consumable, we want to make it centralized, and we want to make it searchable, right? So how do we actually classify documents? And not only classify them, it might be really interesting to build a taxonomy. You can imagine that your documents are coming in and there's some natural structure or hierarchy to these things. Maybe you have a portfolio, and those portfolios you have investments, and in investments you have sub-investments, right? So can we actually get it such that when we classify this thing backwards, we can build this natural taxonomy? So it's really interesting. Then once we have it, let's extract information, right? That's the whole point of the game. Let's actually go in there and say, well, who was the CEO, or what's the invoice date, or what's my annual revenue, right? Can we automatically extract these key terms and put it into a way that easily consumable to the end user, whoever that happens to be? So what we'll do, man, I need my laser pointer. So what we'll do is we'll quickly run through the steps here, right? There's roughly 4 steps where pulling in the data, saving it to the database. We'll really quickly walk through that. That's more of a data engineering problem. And then actually performing the machine intelligence, right? So we'll spend a little more time talking about these 2 things. But we'll start in the first 2 very quickly, just to give you the full flavor. And these are very loose examples. They're not meant to be too deep or give you the exact solutions, right? These are just things you should think through. So step 1, right? I'm sure you're faced with this. You want to take all of your raw PDFs, Excel files, and you want to now put them in a database somehow. But how do you do that, right? It's a terrible problem. So there's things, clicker. So you can actually do this quite nicely in a lot of languages these days, right? Where you have PDF files that are unstructured, you have Word documents, you have Excel files, and you can literally just start extracting information from them, right? There's a lot of really nice open source libraries that you can go in and you could say, okay, here's the PDF, extract for me. Or here's my Excel file, which is already structured, which is very nice, extract that for me. And once I have that extracted, great, right? And this is an oversimplification of the problem, but it's a generalized solution here. So now once we have it extracted, start shoving it into a database. And I told you this is going to be quick for the first 2. So once we start putting things into the database, right, now we want to follow this standard ETL process, right? Extract, transform, and load. So we want to validate and sanitize. So that's always a key thing that we want to think through, right? So how do we escape and make sure that our formats are the same, or our date fields are the same, or how do we actually go through and clean these things in a meaningful way? So you're really going to want to think through this process of things. One of the big issues that people run into is once you start combining your data sources with a lot of other data sources, you're going to get a lot of deduplicated or duplicated records. Right, and this is a huge issue in the healthcare space where you say, hey, this is John Smith from Arkansas who lived here from 2008. But now I see John Smith is living in New Jersey. Is that the same John Smith? So how do you actually, once you're forming your data and taking new metadata together, deduplicate these records in a meaningful way? This is actually a really big challenge. I don't know if anybody in the room is facing it, but it's not a trivial problem to solve, and a lot of industries are trying to tackle that. Okay, one more quick one, then we'll get to something a little more fun. Okay. So the last step, right, we've kind of done our ETL process. We have that. Now we literally want to pick our database. So you should think through, is this structured? Is this unstructured? How do we actually want to shove this thing into a memory layer? So you can think things like Redis if you're using time series, or if it's unstructured, you can think of things like Mongo or Cassandra. But general, there's nothing too magical here, right? Think about it from your use case. What are you guys doing? What solution works best? What's scalable? How much of this stuff do I have? Is it streaming? Is it batched? Right? If you ask those basic type of questions, you should say, okay, this is the solution that makes sense. Okay. Sounds good. Use that a laser pointer? Oh, see? If you ask for things. Thank you very much. There we go. Now I probably won't even use it. All right, where are we? Okay. Now, we did our OCR, we extracted, we put it into a database. Now we actually want to do the machine learning part of you. So I'm going to spend 3 minutes, no more, talking about what machine learning is. I'm assuming everybody in the room knows it, but if you don't, very quickly going to describe it. If you do, also going to describe it. So just bear with me for 3 minutes. So machine learning, I'm going to use my laser pointer. Machine learning is basically just programming a computer to optimize some kind of performance metric to learn based on prior example, right? Give me a whole bunch of prior examples, prior data. I'm going to generalize that data such that I can learn more in the future, right? And why do you want to do that? You could do that for things like regression, meaning I know historical how much a house costs given the functions of number of bathrooms or bedrooms or square footage, and I can predict into the future how much a house will cost. Or I can classify markets, right? This is a bull market or a bear market, right? And I can start actually saying, oh, from a stock trading perspective, I can actually make predictions now if I should buy or sell. So one of the questions that we get asked a lot is, well, if you're here trying to think, does my company need machine learning? Do I need to be doing these things? The answer to all of you is absolutely, that's not always the case, right? There is no need to use machine learning to calculate things like your payroll, right? Or other very kind of traditional problems that you can solve with probably multiplication and subtraction, right? Leave that to addition and subtraction. There definitely are a lot of problems that do need it, right? You know, Google, GE, whoever else, Uber, they're driving autonomous cars. Yeah, that needs machine learning, right? So there's definitely a place for it, but there's not. So you should probably really think that through before you start designing large systems around it. All right, almost done here. So we want to use it when patterns exist in our data, right? When patterns exist and we don't know what they are, that's a prime place for our machine learnings to come in, right? Because if the patterns do exist and we can pinpoint them, then we can actually probably write some mathematical function to them, right? We can represent it in some kind of, I don't know, algebraic formula or something and solve it directly. So that doesn't help us too much. Okay, last one. So why is machine learning hard, right? You see a lot of people out there today, they have nice algorithms, it's all packaged up, and it makes it look really easy. But in fact, it's actually really not, especially when we're talking from the NLP perspective, right? So this is an actual true sign, right? Angry Whopper, all fountain drinks 98 cents, buses welcome, right? Which is a ridiculous kind of statement and something to put out, and this is a Burger King actual sign. And if you read this, this is extremely ambiguous. So if as a human, right, we see this and we do a lot of thinking to understand what this is actually saying, right? There's a lot of information here, but on the surface it looks completely ridiculous, right? Like, is there something about my Whopper that actually makes it angry? Or the fact that fountain drinks are 98 cents, to me, that's actually really inexpensive, right? So that's a good deal. And buses are welcome. Well, buses actually aren't welcome. The people on the buses are welcome, but the fact that the bus is in my shop, right, that's not really a welcoming thing. So the fact is what our machine learning needs to do from the learning of the language perspective is extremely difficult, right? It needs to take how poor we speak and how we write things and understand this, right? So it's actually a very complicated problem. Okay, so we've gotten through that. So now we have everything together. We understand on the surface what machine learning is trying to do. Now let's actually do something, right? So we want to automatically sort and classify these documents, right? We're going to build a taxonomy. We're going to extract some information. We might even do some really sophisticated things like summarizing our documents. You can imagine you have a 100-page document, right? If you're a real estate agent or something and you want to condense all of this information into 1 or 2 paragraphs, right? That's an extremely challenging problem, but it's something that people are trying to solve these days. So the initial kind of language modeling comes back from our old friend Bayes, right? So, I don't know, undergraduate math or high school math, depending on, I guess, how good of a student you were. I didn't get there in high school. We learned about Bayes' theorem, right? So Bayes says, okay, we have some probability of something happening. What is the probability of my event given these other probabilities? And the first place that we really saw this from a machine learning perspective was around these spam filters, right? In the early 90s or whenever it was, the Prince of Nigeria would email us and say, here's $10 million. Do you want to send me your bank information? And there's companies that spun up that really said, okay, we are going to try to model these emails or the languages in these emails to predict if something's spam. So the way that it works back then, and then we'll look at some of the things people do now, is they literally took each word and assigned a probability to it, given the occurrence of something else happening. So the fact that congratulations, this is the Prince of Nigeria emailing you, here's a lot of money, happens in roughly 1/10 of all spam emails, 0.01% in all actually good emails, because sometimes grandma emails us and she says, oh, congratulations, you gave a talk today, right? And it also happens that 4/10 of emails are all spam. So when you kind of do the math out here, you can literally solve and say, well, maybe you can't solve. Oh, there it is. Oh, hold on. Right, you can literally write out in long form the actual probability of this thing being spam, right? But that's a ridiculous process, right? We're now trying to solve a conditional probability across all permutations of the English language, right? To solve this thing in long form is really, really difficult. So that's what people used to do when we were looking at classifying emails. So more traditionally, right, we've kind of taken away from that probabilistic approach, And now we do things in a very different type of fashion. So one of the kind of ways that a lot of people are still solving, right? We're not even talking about neural networks or anything fancy yet. A lot of people, especially in the finance world, are still really thinking about things in this representation called bag of words. And what a bag of words does when we're trying to classify things is it creates a matrix like this. And the matrix says, okay, here are all my documents. And for each one of the documents, I write out my terms, right? Terms could be words like I, them, he, she. And you literally just start counting. How many times does an individual word get put into an individual document? This one is 10, 1, and so forth. And you create this matrix of the number of word frequencies. And it turns out that when we're creating a machine learning algorithm, this kind of feature representation, this TI-IDF matrix, is an extremely powerful representation of what the meaning of that text actually means. Okay? And what you want to do is you don't want to just look at individual words, right? Because if you just said I or them or he, you don't really get the understanding of how it translates to a larger sentence. So if you start saying like I ran or she slept or he leapt, those are terrible examples, right? You can start to understand the actual meaning of the words. So if you do things n equals 2, meaning 2 consecutive words, shove that in and create your features around it. It's actually a really powerful technique, and it's a very simple technique. So here's just a silly example, right? I do not like eggs in my file. I do not like them in any style. I will not take them fried or boiled. I don't know why we keep using this. This is the worst sentence ever. But what you can see is literally in a few lines of NLTK or whatever you're using, you can create the entire feature matrix that you're going to need in your machine learning algorithms. So here's a pretty simple example. So this is an actual real example that you can use. This is using abstracts from PubMed. So PubMed is just somewhere where you put a bunch of medical abstracts. The idea was to take all of these articles, right? So a document classification of 4 million journal articles and classify them into whooping cough, chronic cough, and AIDS, right? So literally in a couple lines of Python, we're going to solve the entire problem, right? So we download using Beautiful Soup, which is Google's kind of nice HTML parser. If you guys don't know Beautiful Soup, it's a really nice library you should look at. It takes it in, it reads the raw text, it cleans it up a bit, it converts it to lowercase, right? So these are basically our step 1, step 2. It shoves it into a pandas library, right? So we're at maybe 7 or 8 lines of useful code here. We then create our features, right? So are we all familiar with pandas? This is what it looks like. So you can see the raw abstracts, the classes associated to each abstract. So here's our training set. We build our feature set, right? So how do we actually build these features? We create a count vectorizer, which is our bag of words. And that's all we have to do, literally about 4 lines of code. And then we shove it into a random forest algorithm, right? And that's it, right? So we load up scikit-learn, put it into a random forest algorithm, and hit fit. And that's it, and then predict. And what you get out of it is a confusion matrix, right? So literally in about 10 to 15 lines of Python code, you've now taken 4 million journal abstracts that you knew nothing about beforehand, and you can get an accuracy, or this is kind of contrived, but around 91% predicting AIDS, 77% predicting whooping cough, and 65% for chronic cough, right? Literally a couple lines of code. Now you're going to say, okay, well, that seems very simple. Does this solve all problems? Well, it doesn't solve all problems. And now what happens if we want to actually get this any better? Right? So maybe you are working and you have to show this to your boss and says, well, that doesn't give me anything because it's only 65% accurate. Now you need to improve these models. And of course, that's where all the magic happens, right? So at that point, you really need to start thinking about, are there better features? Are there better algorithms? How do I tune my algorithms? Are there more sophisticated things like deep learning networks, which we'll talk about in a little bit, and all sorts of things. Right? But when you do things like this, you can create really quick baselines to benchmark how well your algorithms do and how quick and powerful you can get to that point. So I always suggest doing something simple and then working forwards from there just to give yourself some baselines. Okay, any specific questions yet? Anybody want to stop and chat about something? Nope? All right, we'll keep pushing forward. All right, last bit of NLP. So now that we've classified things together, we want to do something a little more interesting, right? Because classification's okay, but we want to actually start to automatically extract key concepts from these unstructured text, right? So when we're extracting things, right, people, places, products, organizations, this is not confined to only doing things like this. So if you are familiar with NLTK or OpenNLP, a lot of the times the extraction algorithms will allow you just to kind of pull out some things like this or tell you about parts of speech or things like that. What we don't want to do is only assume that we're stuck to here, right? Because there's a lot more interesting things you can do here. Right, so we want to think about how do we actually build custom extraction algorithms such that we can get things like effective contract dates or quarterly revenue or CEO of the company, because when you're that PE manager and you need to aggregate your 1,000 files, you're going to need to do it on a lot of customized categories and not so much about people, places, and things. So the way that works, there was two methodologies, kind of just like our Bayes example. People used to write these really contrived regular expressions where you have all these weird patterns, you have nots and ands and wildcards, and you use these kind of old school Linux technologies, grep and aux and cuts, and you would do things like put together these really terrible constructions, right? So imagine that you worked at a bank or you worked somewhere, and I gave you this. And I said, Mr. X withdrew some money from his checking account on a date, and the account now is overdrawn by $235. How would you go about extracting the key concepts in red using regular expressions? And I'm sure a lot of you have tried this, and it probably was a terrible exercise. Even to think about it just finding US phone numbers, right? This is what the regular expression would look like. So now imagine you have to do this for everything else, right? It's a completely ridiculous exercise. So my advice is don't do that, right? So let's actually throw some machine learning at the problem. No, I don't know. I think we're gonna have to live with the buzz. So from a machine learning perspective, we can do the same thing, right? We can transform, like we did the Bayesian statistics to a bag of words model from our regular expressions to another machine learning model. So how do you do something like that? Again, basically all we want to do is create an interesting set of features, right? And then shove it into a machine learning model. So what are my features going to be, right? If you had to sit down and create features to understand the custom extraction, this microphone. What we would want to start to do is look at features like, well, does this word start with a capital letter? Because maybe that's really interesting. Maybe that tells you it's a pronoun or something. Does it end in an ing? How many numbers does it have in it? What's its part of speech? Can we create some kind of dictionary around them? How many words or letters does it have? What's the word before it? What's the word after it? Can we start to build some overall understanding and construction of that given word such that we can build a machine learning classification algorithm and extract these things automatically, right? So that's what we always want to do when we're thinking about machine learning. So from a modeling perspective, it's always very similar, right? We can take some kind of more traditional, naive Bayes, logistic regression kind of things. We can model it using something called like CRF algorithms or Markov models where we're actually creating some, what do we call it, discriminatory or generative models to function, to formulate these things, right? So these are the types of processes that you're going to really want to think through if you're building out some of your own custom models. And again, right? So here's our example. The problem now is this, right? We have different formats of date. We have different formats of time. They're different people. They're saying different words. How can our algorithm automatically do that, right? And the whole, oh boy, what happened? Well, I think we skipped a slide, sorry. We basically want to be able to do this and extract it automatically, right? So this is the whole point. So building that pipeline of having the features such that we can extract and shoving them into an algorithm, you can do this exactly. This is really powerful kind of thing you're going to do and you're going to want to do when you're thinking about how do you take all your documents and automatically kind of pull information from them. No, I don't know, something weird happened. All right, anybody want to stop, ask questions? Anybody deal with this in their day-to-day life? Yeah, go ahead. You raised your hand, I saw you. All right, no. Okay, all right. We will switch gears. So, off of NLP, kind of. So one of the cooler things that people are doing today, past just kind of looking at how do we classify and extract text, is using kind of social sentiment to really start guiding the way that they interact from a trading perspective or a portfolio's perspective. All right, so the idea is, can we take some kind of social sentiment to compile overall views of the company and the overall consumer sentiment? Right, so for instance, Twitter, right, on Twitter, announces that they've missed their revenue by roughly $30 million. Right? So the idea is, can we actually use machine learning to not only classify what that means, the content, right, our angry Whopper for 98 cents, do we understand that well enough such that we can incorporate it into real-time sentiment indicators into our models? In fact, you can, and there's actually companies spun up to do this in a particular type of problem. Right? So they literally, from a trading perspective, will tell you, oh, I really like the way that the social sentiment for this company or this company is doing. This is Plug Power. I don't even know who that is. Sorry if you're from Plug Power in the room. But you can actually have now buy and sell signals that are very relevant to the way that the social media is interacting with you. And it's not just Twitter. Right? If you're doing this at the professional level, if you're a portfolio manager, if you're a fund manager, if you're trading, you want to look at things not just at Twitter, but from the news, from different SEC filings. One of the really interesting things that people are looking at these days are product and Glassdoor reviews. So imagine that you're looking to invest in, I don't know, Best Buy or whoever they are. You can go on and actually start looking, say, on Amazon or something. What do people say about these products? Right? What is the overall sentiment? Do they give it 5 stars? Do they give it 1 star? What are they saying about it? And how is that going to influence the way that the market's going to move? Glassdoor is actually a really interesting one as well. So Glassdoor kind of gives you insights into how the internals of the company is looking. Are people happy? Are they mad? Are they getting raises? Do they hate the CEO? Do they think he's a good guy or girl? Right? All these things are really going to drive some of the things that you look at from the social perspective. If you're not an investor or a portfolio manager, these exact types of analyses are actually really driving some of the cool things that are being done in HR and recruiting. If you're sitting in HR and you want to figure out who you want to hire, what you can do is you can start looking at resumes, right? And start saying, oh, here are my resumes, or here are my yearly reports that we're getting on our employees, and start to understand, are people enjoying themselves here? Would they be a good fit into my company? And answering all sorts of really interesting questions around there. So this is a really cool thing that's coming up in the financial world and also in a lot of other places such as HR and recruiting. So another interesting topic is called topic modeling. This kind of came out really terrible. Sorry about that. So topics are really powerful ways to understanding what documents are about if you know nothing about those documents. What does that mean? So imagine that I give you, I don't know, 100 different PDF files about something, or maybe they're about academic journals or things like that. What a topic model does is, from an unsupervised perspective, it'll look at everything in your documents and start pulling out, these are key groups of words that are representing what's happening inside these documents. So for instance, this is some biological text, right? And all you do is you kind of throw these unsupervised topic models at it, and it starts to say, oh, look, the first one is about something about genes and DNA. The second thing is about life and evolving, right? So maybe some evolutionary. And the third one is about some kind of neuroscience, and the fourth one's about computers. And what you can do is you can start understanding from a really large scale the general understanding and general kind of summarization of what these documents are telling us. So why do you care about that, right? What does that do for me? Oops. So if you're an investor, if you're a portfolio investor, if you're looking at large-scale documents, you can start to spot, for instance, historical trends in investments, right? If you literally took all the papers, and if you want to know where you should focus your intention, who you should start buying from, you can do this from a topic modeling perspective and say, oh, whatever happens in topic 3, maybe that is investing in new energy companies, is on the rise, right? At least from the literature. So we really think that people are going to be investing heavily here. So you kind of can look at these historical trends and make really interesting statements, right? You could also do things like sentiment analysis or summarization like we talked about before. Right, so this is just another example of some of the things that you can explore from the NLP perspective. All right. We're done with text. Anybody questions on text before we move forward? No? Okay. All right, so some basic time series before we talk more fun time series. So time series, right? What is a time series? I'm sure we all know this, but time series are basically just periodic observations in time. They're usually evenly spaced apart, and they're usually something that we call stationary, which we'll come back to. So why does anybody care about time series? Why does anybody care about anything that happens in a temporal aspect? Well, if you're in finance, you care about it a lot because you're looking at revenue forecasting, you're looking at stock prediction, which we'll talk about in a little bit. But you could also be doing a lot of things, right? From a demand forecasting or strategic planning standpoint, right? How many products do I need to stock on my shelves? How many employees do I need to hire, right? There's a lot of different things that you can think of from a time series perspective, right? Inside finance and outside of finance. So how do you actually do this, right? What is the methodology used in finance and other places to deal with these kind of problems? So here's just a silly example, and we'll kind of work through some of the techniques. So this is an example of actually measles in the 1940s and 50s. And measles is actually really weird. For some reason, there's these kind of 2-year periodicity. So how do you actually go about and forecast future values here, right? So there's actually a lot of nice functions if you want to do this in a kind of more traditional approach in Python and R. And some of these kind of nice approaches to do this kind of automatically for you are things like your seasonal decompositions, your Holt-Winters exponential smoothing, or your ARIMA models. And basically what you would get, right, you would get some here is all my historical data, and now here is all my new data that I'm going to predict out. You'll get something about uncertainty bars, so you can go to your boss when they ask you how good is this prediction, and you can tell them, oh, it's some 95% accurate, or things like that. Right, but this only solves a very small class of problems, right? This isn't going to really tackle something difficult. So the question is, what do we do when this doesn't work, right? I'm sure we've all, if anybody works on these types of problems, you've thrown something that you think is easy to predict into your R or your Python, and you say, oh, use ARIMA or use, Holt-Winters smoothing, and it comes back garbage, right? So what's the next process that people do, right? So this is where things get interesting. So for instance, let's just take stock trading, right? It doesn't have to be stock trading, it could be anything. So there's 2 types of domains we can work in when we're in time series, right? There's a time domain, but there's also a frequency domain. And we want to look at how these things evolve as a function of not just short, but also long-term trends. So let's think of this as a classification problem, but it doesn't really matter. The idea is I give you a pattern, and the question is, can you spot clear signals when we should buy or sell, right? Where's the kind of market bullish or bearish? And if we were going to write a classification algorithm, you would start identifying different places, like, oh, we definitely want to sell when we're high and buy when we're low, but how do we do that? So there's a couple ways you can do that. If you're looking at it from the time domain, you can start generating features, and then obviously take those features and put it into your own algorithm. And a lot of the features that you're going to generate are based on these sliding windows, right? Here is a length of time. I need to only look backwards. If you look forward, you're cheating. If I look backwards in time, what does my lag parameter look like? What does my rolling means look like? Or what does my standard deviations look like, right? There's all these kind of custom features that you have to create. And the problem is, especially when you're dealing with finance or something like that, you have to be really smart about the features that you're building, right? The gentleman in here before me, I walked in late, he was talking about that as well, right? There's a small set of features that are going to be really powerful when you're doing really complicated time series predictions. So how do you know which one of these are really expressive and it'll give you a good overall accuracy value? So if we don't look at it from the time domain, one of the nice things that I like to do is transform all my time problems actually into an image problem. Okay? So if you take your time domain out of the equation and you translate it into a spectrogram, you've now actually entered a completely new set of problems. You've actually turned it into an image problem, and we can start to do image analysis, right? And this is what we'll talk about in a little bit with our kind of neural networks type of things. But once you're in an image, now you can do some cooler things, right? You can run your convolutional neural networks on this guy. You can look at other things like fast Fourier transform or continuous wavelength transform. And there's no more real of this windowing effect. You kind of extract out that point of the problem, right? So this is a really cool kind of interesting approach that you can take if you're having problems kind of solving some of these issues with your time series. So, well, now what do you do when that doesn't work? Now you're in trouble. So that leads us to our next point. Anybody specific time series questions before we come back to it in a couple minutes? Nope. Yeah, go ahead.
Series information.
Sorry, say it again. Now I can hear you.
Can this work with multiple time series? Set like information, like multiple pictures with different,
Yep.
frequencies.
Yeah, so you can do that exactly. So a lot of the times, for instance, you might have multiple signals or multiple different types of information, like not just time information, but text information or other things like that. So everything that you're doing, if it's in the frequency or the time domain, you can stack onto each other as different types of features. So you could have features that are image-based, features that are time-based, features that are natural language-based, and shove them all into a common algorithm to make it more robust, right? So by no means are these only inclusive of themselves. You should always think of these as only a single set of features, and we need to explore all the feature space. Make sense? Cool. All right. Yep, please. Yep.
Can you just explain more with that, like, color one, the blue, the yellow,
Yeah.
the red? I don't really understand what that graph is. Thank you.
Sorry. Let's see. Well, I don't have a good thing coming into it. So basically what happens is when you have a time series, right, you'll have, I wish I had a plot. So you convert it to a spectrogram, right? And this is a power spectrum at this point. So you can see, let me come over here. It's still as a function of time, right? So we're still now looking at 210 seconds. And you can see what frequency spectrum each of these little time windows are in. So this basically tells us what our power spectrum is of that time series slice that we're looking at. Does that make sense? I don't know where you went. Kind of. Do you know anything about power spectrums and how that converts? Okay, we can move on. How about we come after and we'll talk about the math of the conversion. Anybody else? I saw two hands. Nope, they got shy or had the same question. Okay, so deep learning. So particularly interesting topic. So before we talk about what deep learning is, let's think about why we created it in the first place. So our brain is actually this just large connection of neurons, right? We have roughly, 20 billion, if I wrote my number correct, neurons. I think women have a little bit more, which makes sense. You're usually much smarter. But what happens is you have these 20 billion neurons, and the strengths of these connections represent some kind of long-term knowledge, right? If we have a lot of these neurons, they're really strongly connected, we kind of build these memories or this knowledge. So what happens is, if I am an image coming in, right, I'm looking across the room and I'm seeing all of you, the image comes in, it hits my retina, it does some stuff, it goes into my neurons. The first stop, we start thinking, oh, I can now start representing this image in some way. I see it as a bunch of edges in very rough shapes. The image continues to travel. I now start to formulate different groups or structures on this image. If I keep traveling to different neurons, kind of later down in the hierarchical scheme, I can start to putting together some high-level object description, like that's your face, this is your body, here is your hand. And then we finally get to the end where we make a decision off of that, and then we fire some signal to your hand to do something. Right? So the whole point of what your brain is doing is it kind of stacks these neurons onto each other, where the first level is very sensitive to things like edges and shapes, and then the final end layers are really kind of sensitive to these complex structures and can start to tell you what you need to do with the associated action. So the idea of neural networks and deep learning and why it's interesting is it actually kind of reconstructs this entire thing here, right? It tries to, from an algorithmic point of view, start doing what your brain is actually doing. And what it does is when we sit down and write our neural networks, if anybody's familiar with the actual insides of a neural network, right, we have an input layer, which is our traditional image or text or time series. It doesn't really matter. But we start kind of stacking these hidden layers in between it, right? And these people will call them different things like dropout layers or convolutional layers, but it doesn't really matter. But we just keep stacking and stacking and stacking, and then at the out, we have an output, right, which is our standard prediction thing. So each new layer that we put inside of our graph here represents more things that our brain would have done, right? So it, in theory, is trying to be smarter and smarter about the task that it's asked to accomplish, right? So the beauty of deep learning is, right, we've been talking about from the NLP and the time series stuff, you always have to do this, which is terrible, right? We take some input, we want to do some output, but to get there, we spend a lot of time feature engineering. If anybody does machine learning here, and they work with time series, they work with images pre-deep learning, you probably spend 99% of your time thinking about features. So this costs you a lot of time and a lot of headache. So deep learning actually takes the different approach, right? It says, okay, give me the entire image. I will self-learn myself what the concept of these images or the text mean. I will auto-learn that for myself, and then I'll spit out the final result, which is beautiful. It takes a little bit of time, but then it kind of extracts away the issue that we have of feature engineering because it kind of does it by itself. So what does that look like? So this is something called convolutional neural networks. So convolutional neural networks takes an image, it shoves it in, it does all sorts of kind of cool intermediate layers, but at the end of the day, all it's doing is the same thing as our brain does. In the very first few things, it's kind of just learning these weird edges and shapes and kind of weird things over here. As it kind of gets further down the line, it starts to understand things like structure or overall parts of the system. And then at the very, very end, it kind of concatenates all these things together to recognize the overall object in the image, right? So it's exactly how we described our brain doing. So if we take our cat, right, and we take the image of our cat and we shove it through all the different layers, it's precisely what's happening, right? Here's the first part of our brain, second, third, fourth, blah, blah, blah. And as we go through, the deep learning will basically be able to say, oh, I get it, that's a cat, right? For faces or humans, it's the same exact thing, right? We take all our humans, we shove it in, we get some edges, we get some noses, we get some eyes, we get some overall face structures, and at the end of it, we're able to detect humans or people or objects, right? So it's a really interesting and powerful technique. So why go through this, right? So there's a class of algorithms called long short-term memory cells, which learn how to map large input sequences to output sequences, right? So this is a really cool thing. So let's imagine that we have some kind of sequence. They could be different relationships, meaning one-to-one or one-to-many, and we want to know the output of these sequences given their entire history of inputs. So what is this used for? Well, you can imagine it's very well suited for historical time series data, right? So the question is, if my ARIMA model didn't work, and my fast Fourier transform or my other feature generated models don't work, where do we turn? One of the really interesting things to look at is how do you now map and do time series predictions from a neural network perspective, right? So LSTM is an interesting place for you to try. So you can try doing things like this. And it works really well because it looks and understands really long time lags of unknown sizes between events. So this is a very prime candidate now if you want to talk about more modern ways that people are approaching stock market prediction, right? This is not something that we're going to do in high frequency trading, but if we're looking at longer movements in the markets, different funds or different whatever we're trying to predict, even from a forecasting perspective, this is a really kind of interesting way to attack the problem. And it basically is our standard time series. It builds a neural network around the historical lag, which we don't need to pre-specify. It kind of learns, and then it'll start making predictions forward for us. So if your ARIMA doesn't work, if your features don't work, give this a shot. Maybe this works. But as Malcolm kind of asked before, what do you do when do you only look at one? No, look at them all. Put them all together. Build an ensemble. See if it actually makes anything more useful for us. OK. Now, we actually live in a day where we don't need to only look at our time series, right? There's a lot of more interesting information we can add in if we're looking at, we call it stock prediction, but it could be anything, right? So how do we couple multiple layers of information together? So in fact, weather data from a finance or an insurance perspective is really interesting at driving customer behavior, right? So how many people will show up at a store or a promotion is a huge function of the weather. So you could actually start modeling these things. So if you're sitting down and your boss or whoever, you're the boss, you want to determine who's going to come out if I do this? Or what is the risk of doing something like this? You can start adding in some really interesting types of data sets to make your accuracy and your predictions better and better. One of the things that you'll see out there that people are claiming that they do, I don't know how much of this is true, but it's actually a really interesting use case, is instead of looking at weather patterns to predict like crop yields or anything like that, they're actually taking satellites, and they take the satellites over, say, Best Buy or Macy's parking lot, and they say, how many cars are in the parking lot? Right? So you actually have a lot of people claiming that they do things like that, which I hope they do because it'd be an interesting problem. And they claim that they can detect the number of vehicles there, which is okay, we can do something like that. And they use this as an indicator to determine how many people are actually going to be coming to those businesses and if that's a viable thing for them to invest in. Right? So from an object detection standpoint, what they do is they basically take these satellites, they build these convolutional neural networks around them, and they start being able to map all the different, cars or whatever it is in the parking lot, count them up and say, okay, I see traffic's increasing or traffic's decreasing. So this is a very kind of modern thing that people are doing, especially from the kind of fund management or portfolio prediction standpoint. Okay, any questions on deep learning, using LSTMs, CNNs? We didn't go too deep into them, but anybody have questions? Yes, sir.
Hold on a sec.
So for the deep learning, we should have for the vision or NLP a lot of data. So I'm wondering how much data should we have for the time series to do the LSTM?
Yeah, so time series you're usually plagued because historical data only goes back so far. You might only have 5 years worth of useful tick information or 10 years or however the granularity you're working. So that sometimes is a limit with the time series. If you're doing computer vision, right, that's another problem. So normally computer vision, you can get a lot of these satellite images or any images that you're looking at. The problem is you need to tag these, right? So getting somebody to sit down and hand label these things, right, you literally would need to go in. So this is object detection, right? So you literally would need to go in and label all of these and draw coordinates around them and build a large training set. You usually need a few tens of thousands of images. It depends on how diverse the data set is, if you're only looking for cars or if you're looking for all sorts of different things, right? You might be looking for roads or crops or all sorts of different objects, but usually in the tens of thousands of images. There are some large-scale solutions out there if you're doing this. You guys can go talk with NVIDIA. They have this really nice kind of computing platform out there. If you're doing this in a serious sense and you have large images, you're going to really need some optimal performance. A single GPU won't do this. You guys are going to need some kind of a large-scale architecture. So it's definitely costly from a time perspective, but it's worthwhile. You can do some really interesting things.
So LSTM is good because the data is sequential. I'm wondering, have you tried the kind of Bayesian or hidden Markov chain?
Of course.
How it works compared to the LSTM?
Of course. These are just general approaches, right? I wouldn't suggest you only looking at one approach. That's kind of the naive approach to take. You should say, what's my problem? What are the approaches? What are the trade-offs, right? Because each of these operate well in different kind of phase spaces. And just because your neural network works well, maybe it's offset really nicely by an XGBoost algorithm. And you want to shove those together in a meaningful way because they capture different amounts of information. You don't want to only use algorithms that capture one set of information over and over again because it's not going to generalize. The whole point, especially if you're doing stock market prediction, is you need to generalize this thing as much as possible. Otherwise, it's not going to work past the next week, and then you're going to lose a lot of money.
I have a question, please.
I don't see where
Here.
Hi.
Hi. I wanted to ask, how do you incorporate different features of different type, like you gave, like you said you use also sequences like time series, but
Sure.
also things like this, like the
Sure.
number of cars?
So let's imagine that, let's just keep using the stock prediction example, right? We're looking to invest in Apple, I don't know, or Best Buy. I keep using Best Buy. We're looking to invest in Best Buy. I can look from a time series perspective and say, oh, I think Best Buy's stock is going to go up or go down. That's one way. I've read all of the news articles and I see the overall sentiment for the Best Buy is going to go up. But I looked at their parking lot and they have no more traffic. So what you've done essentially is made 3 predictions independently. And now, if anybody's familiar, you want to add some overall layer on top of that.
Stacking.
Exactly. So you want to add a second stacking layer, right? If you guys work in Kaggle competitions, this is basically what you build these crazy big things. But yeah, it's a stacking problem, not just stacking random models, but stacking different data type models. It's the same exact principle.
Thank you.
Sure. Anybody else? Before we totally change gears? Nope. We're way ahead of time, so you can ask. Okay. So portfolios. So portfolio optimization, right? So what's my portfolio? So a portfolio consists of things such as assets and investment capital, right? So let's imagine that I'm a very rich fund manager, or somebody gave me a lot of money, so somebody else is really rich. I have a few $100 million that I need to invest. I invest in things like stocks or bonds or whatever they happen to be. And then I also have some kind of free capital sitting around. The decision that I need to make is, how do I know how much capital should be invested into each asset, right? It's actually a very complicated question to ask because there's a lot of things that go into this kind of decision, right? What are the constraints that I need to impose? How diversified do I need to be, right? If I invest all into one company and it goes under, well, I'm a pretty bad fund manager and I'd probably get fired. How much exposure do I need to have to different assets? What are the transaction costs? What are the foreign exchange costs? And all sorts of different things. Right, so when you look at it from this perspective, you really can't just sit down and say, okay, here's the optimal place, right? This is not some mathematical function that we can just solve explicitly. What we want to do is we want to, develop some kind of search optimization algorithm to kind of say, here is where I want to operate to be as safe as possible from an investment risk portfolio. So whenever we're doing portfolio optimization, basically, it works by forecasting, right? Same kind of time series forecasting as we're talking about, the expected risk and return of each asset in that portfolio. So how do we do that, right? So it's the same kind of algorithmic approach. So we use these forecasts. So we take all of our assets or whatever we're doing. We want to forecast that. That acts as inputs into our model. And then we want to determine how much capital, right, how much do we want to actually invest into each one of these assets such that we maximize some adjusted rate of return or something of that nature, right? You get to predict what you want to, or choose what you want to maximize. The problem is, of course, if your forecasts are terrible, everything else is going to be terrible. So it goes back to our time series problem. Do good at forecasting such that something like this is meaningful. Otherwise, you're kind of just shooting yourself in the foot. So, I don't know, about 60 years or so ago, this became known as modern portfolio theory. So Professor Harry Markowitz, back in '52, looked at assets as these kind of normally distributed symmetric measures of risk. So if any kind of physicists or engineers are in the room, right, we can think of this as our kind of particle in a box, right? We have these things floating around in space. They have some kind of distribution. How do we actually take this distribution and find some local minima, right? So a lot of the work that he did was kind of derivative off of some of the kind of physics and engineering models of the day. So that was fine and dandy. Some of the extensions, right, some of the kind of more modern things are called, I forget, is it postmodern portfolio theory, which is a really terrible way to say it, because what's more modern than postmodern? But they include these kind of non-normal distributions, right? Because what people say is, okay, if I look at the market, it's really not symmetric, right? My risk and my reward aren't really symmetric. We could actually have some kind of tailed distribution, right? So that was one of the things that came at postmodern. Basically, we added a tail to it. And then the question is, okay, now I have all these particles in a boxes and everything kind of floating around in space. How do I actually solve that matrix equation? So there's some things out there today that you can do that, right? There's things called random matrix theories where you throw all these things into a large matrix and you start solving them in a kind of really complex mathematical way. Or we steal some more things from physics and engineering, such as particle swarm optimizations, where basically, think of it as like bees kind of flying around. How does that kind of, those bees know where to navigate and get to? Things called simulated annealing, topological data analysis is a really interesting new kind of clustering analysis that's done really heavily in neuroscience, right? So you can do some really interesting things in this space of saying, how do I take my data from an unsupervised perspective and start to understand the nature of the optimization problem. So from a clustering perspective, a lot of the new, like I just said, right, a lot of the new things are based off of this, right? Instead of looking at assets as a single entity, we kind of look at them as a cluster of entities. And this is done for some reasons, but basically, we put an emphasis on the matrix, so our random matrix theory, and we solve this in some meaningful way to get our overall assets, or this is our overall portfolio that we want to invest in. The problem with any of this, portfolio theory is still kind of, let's see, what happened here? This thing was like dancing around. Oh. So portfolios are still really subject to these kind of mathematical anomalies, right? Sometimes market crashes. Can we actually predict these things? And that's not really good. It doesn't really work so well. So even though you might have some really good representation of your portfolio, things still can go, kind of hit the fan, and then we're left with not doing so well and losing a whole bunch of money. All right, we are way early. So that's the talk. Anybody have questions? Yes.
Going back to the methods.
Yep.
For example, the parking lot example.
Sure.
It looks very clever, but how do you have estimate on how accurate it is?
So accurate can mean two things here. You can ask about how accurate it is at detecting cars, or you can ask how accurate cars are at predicting.
At predicting stock prices, yeah.
So I didn't do this. I don't know. That's what I was saying in the beginning. There are companies that claim that it is actually indicative of market movements. What we do as a company is we do the detection of the cars, but we actually have never used it from a trading perspective of using the cars to then predict the markets. So I don't have an answer for you. I mean, people are just making those general claims. If anybody in the room knows, they can answer. Go ahead, sir.
So, in your view, like deep learning, you try to eliminate feature engineering part. But is it if we so in your deep learning part, try to eliminate the feature engineering part. But if you include feature engineering and then like deep learning, such as LSTM,
Yep.
is it to improve the performance?
Usually, anytime you're starting to stack algorithms together in a meaningful way, you're going to improve the generalization of the methods. And that's what you really care about, right? If you're back testing or your cross-validation maybe stays the same, maybe doesn't look so great in terms of improvement, what normally happens anyway is your generalization of that for future gets better. So I would always suggest, if applicable, to do it as much as possible and make sure that the algorithms are diverse enough such that it's tackling different things. Right? If you have an LSTM and an XGBoost, also throw in a very simple linear model, because that linear model is actually doing something much different and could do something from a generalization point of view that's really powerful. Make sense? Cool. Oh, way back.
Thank you so much for the presentation, by the way.
Sure.
Just to sort of extend the gentleman's question,
Sure.
What are different ways to stack your algorithms once you know which approaches you use?
So
'Cause
yep.
I feel like there are many different ways.
There's many different ways, of course. Which way is better is a different question from what are the methods. Which way better is something you should cross-validate. What are the methods? So basically, right, there's these two-level stackings where you can take the predictions of each and then either do a naive ensemble of those and just add them up, right? That's the most naive. Or you can actually do the prediction of each and model the prediction as another model, right? So that's actually more powerful because now you're throwing another model, be it logistic regression or XGBoost or another neural network on top of all the predictions. What you could then also do as a absurd kind of thing is take all the model outputs as well as all the feature inputs together and build one more larger network. So you do a bunch of things, but don't do one naively, cross-validate. Yes, sir.
So you mentioned the stock price You mentioned the stock price prediction. So how many days you can predict? 1 day ahead or several days ahead? And what is the accuracy for the prediction?
So that's not a answer I have for you. So I think it depends on what you're trying to do. Some people are looking for very short-term movements, you know, at the minute or second scale. Some people are looking to only close out at the end of every day. Some people are looking to make one investment for a quarter. So it really depends. In terms of accuracy, I mean, accuracy doesn't really make sense in this context because we're talking about prediction in a kind of regression base. You know, you might ask how well somebody's portfolio works. That's a very different type of question.
Okay, thank you very much.
Yep.
So obviously if you have domain-specific knowledge, like you're looking at an image of cars or you're looking at a time series, you apply feature engineering that you know works for that domain. What are the kind of cutting-edge progress is being made with the unsupervised, like you know nothing about the data, you don't have any assumptions to work off of?
So what assumptions are you making when you're doing car predictions?
Well, you would use like a convolutional network classifier usually for something like that.
Yeah, no, but why is that? From a feature engineering perspective, you don't know anything about what features the machine learning algorithm is creating, right?
Right.
So I mean, I think the answer there, if we're talking about deep learning specifically, is you're really just giving it the input. And then your whole goal, right, the real task of deep learning is to produce a network that's meaningful. And you let the network, you let the network determine those features, right? So if we go back here, or wherever we are, the whole point of stacking this thing, or the other one's got a nicer picture, it doesn't matter, right? The whole point of putting these layers together in some meaningful way, right? We have our pooling layers, our convolutional layers, our dropout layers, and stacking them in a meaningful way. That's the whole art of deep learning. It's doing that appropriately and tuning those weights. In terms of what actual features come out of that, that's an automated way that it's doing behind the scenes. So it's kind of a different way to approach the problem, but you're not really dealing with features anymore. You're dealing with architecture.
Thanks.
Sure. Yep.
Thank you for your talk.
Thanks.
So I was wondering, how do you structure the data set when you're using like a time series, of course, as like stock prediction? Is it where like one row is the ticker, and then the first column is, let's say, yesterday's closing price. The second column is the second day prior to the closing price, and how would you structure that?
I mean, you can pretty much treat it in a columnar fashion, right? You have day one or whatever, 9 a.m., 3 p.m., and then you can look, and it depends on how granular you are, right? If you have tick data every minute or every hour, you basically can structure it that way. If you want to do something, right, you kind of can build in an automatic lag of it where you say, here's at 3 p.m., all the things before it, 2:59, all the ways before it, right? So you can kind of build it row by column, just like you would build any other kind of data set. It's the same thing if you're going to shove it into your ARIMA model or anything like that, right? There's a very kind of unique temporal structure, so you can follow the same methodology.
I'm wondering if there's a general practice how to validate time series like analysis, like for example in stock prediction. I wonder if there's additional practice other than cross-validation. And
so cross-validation is not what you want for your time series?
Of course, yes.
Right, so the issue is you never want to use forward information, and cross-validation mixes it up.
Yes.
If you're doing stock trading in particular, right, you need a good back testing system. And now, not only back testing, you want to do live testing. But let's imagine we're not talking about stocks. Time series in general, right? You have a set of time. And what you can do is you can start cross-validating it. I forget the exact term, but you can look at, say, let's say we have 10 points that we care about. You can look at the first point, right, and do the prediction there and see how it predicts for the next 9. You can then look at the first 2 and see how it predicts for the next 8. 3, 7, blah, 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 right? So you kind of stack. Instead of cross-validating randomly, you cross-validate kind of sequentially. So that's the way you would want to think about it from the time series perspective. Or you could be really simple about it and just take the first 50% of your data as your training, the next 25% as your validation, and then the next 25% after that as your testing, whatever.
So there's not an established system. How
Well,
to
no,
do
it's the
it.
same thing as in cross-validation, right?
Yeah.
How many folds do you use? Do you use stratified, right? Like, there's always multiple methods, and you need to figure out for your problem what's ideal, and you can probably cross-validate your cross-validation in some way.
Thank you.
Sure, go ahead.
Thank you. I think you were referring to k-folds cross-validation.
Not for time series.
Okay, got it. So my question is, might be really reductive, but can you throw some light on what kind of problems, if it's legal for you to share, what kind of functions or models are built from a financial standpoint? So are they leaning towards more on the regression side where you're trying to predict the ticker price at the end of the day or in the next 2 hours, or is it more about classification when we are saying that whether this stock is going to go up or down the next X number of weeks? So just curious on this kind of model definitions that exist in the financial world.
It could be both, honestly. Like there's room for both of those things. It depends on what you're trying to do. So for instance, we do for a futures trading company, and they want to close out all positions by the end of the day. So every day you make your predictions. They do maybe 3 or 4 a day. They see here's the best point to invest, and they say, okay, this is right. There's some percentage that they're happy with where you've made enough over the commission that you have to pay to the exchange, and that's when they decide to make the movement, and then they close out the position at the end of the day. Other people will do it purely on buy-sell signals, right? So you basically take your regression model and you can make it into a classification model, right? Just like we did with our bull versus bear, we kind of just, ups and downs. So it really depends on who's the trader, what they're looking at. I don't think there's a general yes or no to that question. It's pretty much as you would imagine. It depends on what they want to do. Yeah.
Is there any other question? Go.
Yep.
Thanks again. Have you seen applications of sentiment analysis with time series? So like customer feedback and reacting quicker to positive or negative sentiment and how that decays over time?
It's an interesting question. I never really thought of it from a time series perspective, because when I think time series, I guess I'm thinking more traditional sequential points of time. Ask your question again.
So we've had these problems of reacting to negative customer sentiment, right? But then you miss that point over time, right? They're not going to care as much maybe a month later when you interact with them. So
I see.
Yeah.
Sure. I think, right, there's a decay function in the sentiment. I haven't had a problem specifically that looked at a decaying sentiment function, but you can imagine it's very similar to other things like even a propensity or a churn type thing where there's a functional form of happiness or sadness as a function of time, basically. And if it relates to sentiment or whatever you're relating to, yes, it's probably very similar to other types of applications, but never in terms of social for trading perspectives. But it's an interesting thing. I never had thought about it before. Thanks.
Thanks. My question is, do you see a lot of demand from your customers trying to make sense of the models that you create based on the machine?
So, not yes and no. A lot more marketing type of questions. They really care about the sense of the thing. So if you say these people will churn, right, leaving your system, they really care about the why. Like, why are they going to churn? What variables in the model are telling me they are going to churn? Is it because they haven't bought something in 2 weeks because they went to another store? Right? That's really important for them from the business side of view. When we're talking about, stock prediction or a portfolio problem, it's usually too mathematical to deconvolute that way. So you really can't derive meaning. A lot of the meaning you can do based on decision trees or something. So if you're using a really complicated neural network, you lose that. So one of the reasons is I use XGBoost in a lot of modeling, especially for marketing folks, is because you can now answer some of those questions, right? You can start ranking your features and saying, oh, because I see this, and you can start making business logic about it. So indeed, but more so depending on the problem.
Yeah, So one thing I'm thinking about is the impact will be on your confidence in your model, like, and then how much money you will bet on, and also like if there's like a regime change, how
Yep.
can you detect that?
So regime detection is a different type of problem, right? So these are kind of these change point algorithms, if that's what you're asking about.
Can you elaborate on it?
So change detection, if you have, it's almost like an anomaly, right? Where you have, think of anything, right? Sun spikes or stock spikes or something, right? The whole point in change point detection is things are happening and all of a sudden you see a peak, right? So there's some instantaneous something happening there that you want to detect when this thing is going to happen. So is that what you're referring to when you say?
Yeah, so basically you're saying like have a system to catch those type of things and stop trading instead, like, okay.
Right, so that is a viable option, right? But that's a whole set of algorithms designed just to do those kind of change point detections. There's actually some interesting ones out there if you take a look through them.
Any other questions?
No one? Everybody happy? Nobody want to know about tech stuff? That's the fun stuff. All right, thank you guys.